Hello, everyone. Welcome back to the Blockchain Fundamentals webinar, Lecture 4. Today, we'll be talking about interacting with Bitcoin, specifically wallets, mining, and more. Please let me know in the chat if you can hear me. Please let me know if you can see the screen. I'd love to get that feedback. As per usual, please also ask your questions in the Q&A in the chat. We have our wonderful education team monitoring both, and they'll be answering questions. I'll be answering questions. Diego will be answering questions. And also, please join our Facebook group where we upload a recap of the questions and some discussions that are had in the chat in the following week. Hopefully, the education team can send out that link so all of you guys can join. A quick overview of the lecture. First, we'll be talking about types of users in the Bitcoin network. Then we'll go into wallets, wallet mechanics, and then Diego will take over and talk about mining and real-world mining. Just to introduce myself, I'm a computer science student here at Berkeley. This is my second semester in blockchain at Berkeley, where I'm in the education department, and I'll let Diego introduce himself.
Hi everyone, I'm Diego. I'm a senior studying also computer science at UC Berkeley. I've been in the org for about 5 semesters, and I work on the consulting department. Actually, I'm the head of consulting now with Jen, and yeah, super excited for the lecture.
All right, great. Seems like everyone can hear me well and see the screen. So let's get this started. First topic, as I said, will be types of users. Now, in the previous lectures so far in this webinar series, we've been talking about full nodes. These are the nodes that you all know and love. These nodes download the entire history of the blockchain. These nodes mine on the blockchain to introduce new Bitcoin supply into the system. These nodes are connected to the network, and yeah, these nodes are the nodes that we've been referring to when we say full nodes. But this raises a question, like what if I want to send my friend Diego some Bitcoin from my mobile phone? Does that mean that my phone has to download the entire blockchain? Does that mean that my phone has to mine on the network to actually send Bitcoin just to my friend? That would be a huge issue, and luckily that's not the case, because not every node on the network is a miner, as you can see on the screen. Not every node on the network downloads the entire history of the blockchain, because thank God, because my phone doesn't even have 280 gigabytes. Not every client is directly connected to the network, and not every client has a wallet. Alongside full nodes in the Bitcoin network are light nodes, also known as SPV nodes. And so these nodes, instead of downloading the entire history of the blockchain, will just ask their peer nodes for block headers. And they'll use these block headers to verify that a transaction is valid or invalid. SPV nodes do this by using a method called simple payment verification. And this is used to verify if a particular transaction is included in a block without downloading the entire block. And as you can imagine, this means you don't have to download the entire blockchain. This keeps track of your transactions and only your transactions, and thus they're also known as lightweight or thin clients. So how does it do this? How is it able to verify transactions if it doesn't have the blockchain to check against? Well, SPV nodes will ask their peer nodes for block headers of blocks. And the assumption is that these incoming blocks from its peers are not from a false chain. We're able to assume this by connecting to many different nodes. So if I'm an SPV node, I'll connect to a node over there and over there. And the more nodes I connect to, the more likely it is that I can find out if a block given to me is not of the honest chain. In the long term, this chain that the chain that we're getting the blocks from is probably honest, and this is the trade-off that you'll face when you're trying to decide between running a full node or running an SPV node. You know, you don't have the entire history of the blockchain downloaded, but you don't have the entire history of the blockchain downloaded. So while that's less storage, you also have to trust in your peer nodes to actually send you the correct data to verify your transaction against. And so how is it able to do this? Well, like I said, we're given these block headers from our peer nodes, and these block headers, if you imagine from the last lecture, contain some very important metadata about the block. It has, as you can see in the picture to the right, the previous hash pointer of the previous block. It contains the nonce, which is the puzzle that we have to figure out, or not we, because we're SPV nodes, but other full nodes when they're mining. And most importantly, these block headers contain the Merkle root. Now, if you remember, the Merkle root is the root of the Merkle tree, and the Merkle tree at its bottommost layer had all the transactions, and the other levels of the tree were just the hashes of those transactions. And so using this Merkle root that we're given from our pure nodes, given an incoming transaction, we being an SPV node, can use a Merkle proof of inclusion algorithm to make sure that a transaction is accounted for in a block. If the Merkle root with the transaction that we're checking matches the Merkle root in the block, then we can know that this transaction is valid. There are other types of nodes on the Bitcoin network other than just these two, but we'll be worrying about these two for the rest of this lecture. Are there any questions so far about different types of nodes? Please put in the chat or Q&A. Looks like we're good. I'll give it a couple more seconds just to see if anyone has any questions. Cool. Now let's get into the meat of the lecture. What are wallets? To put it simply, wallets hold your private and public keys. Now, this may be surprising because in the real world, wallets hold our cash. It holds our currency. This isn't the case in Bitcoin because Bitcoin, for one, isn't a physical currency, and for two, there isn't really a digital representation of Bitcoin. It's not like a string of letters or some code or something. However, our identities as users on the Bitcoin blockchain does have a digital representation, and this digital representation is our public key and private key pair. Remember, the identity of users in the Bitcoin network is just their private key. Bitcoin transactions come from private keys. Bitcoin transactions come from public keys, and they go to other public keys. And so how do you prove to everyone that has the Bitcoin blockchain downloaded that you own a certain amount of Bitcoin? Well, you have to prove that you are the public key that Bitcoin was sent to. And how do you do this? Using your private key. This is how wallets are able to know how much Bitcoin you own. It has access to your public key, and then it checks the distributed ledger to see how much Bitcoin has been sent to the address, how much Bitcoin has left the address, does some math behind the scenes, and it shows you that sum of Bitcoin that you yourself own. So just to reiterate one more time, wallets at its core just store private and public key pairs. And so by doing this, it provides a user interface to the blockchain. Yeah, this is kind of like the layer in between you as a user and blockchain as the tech. Bitcoin wallets keep track of your private key. They can store, send, receive, and list transactions, and maybe some other fancy functionalities based on implementation that we'll take a look at later. And so now that we know what Bitcoin wallets are, let's look at some examples. And to do this, I want to use this cool tool I found or identified. Bitcoin.org provides it to us. I encourage everyone watching to check out this link. Hopefully, maybe one of the education members can put into the chat for easy access. I encourage you guys to follow along. Basically, Bitcoin.org created this wizard that allows you to, that helps you choose a wallet that's right for your needs. And so I'm going to exit out of this presentation and let's go take a look at the website. This is what that website looks like. Choose your Bitcoin wallet. Let's help you find a Bitcoin wallet. So let's check this out. Let's click next. And just like in the previous example, I want to send my friend Diego some Bitcoin. Maybe I owe him some money and for some reason I want to send it to him in Bitcoin. I have an Apple device, so I'll click Apple. Let's click next. Let's say I'm a new user. I don't really know that much about Bitcoin and I just want a simple app to be able to send Bitcoin. A lot of options. You can feel free to check out these options for yourself, but I'm just going to click next for this and also next for this section. And we're outputted with these two options we can choose from. I'm just going to click on BRD and let's check out what this is. BRD is one of the easiest wallets for new Bitcoin users. Okay, cool. Extremely secure. We like that. Connects directly to the Bitcoin network, device built-in hardware, yada, yada, yada. Let's take a look at this picture. And so we see this picture. This is a screenshot of the app. And I don't know, to me, it kind of seems like an orange PayPal. We see like a send button, a receive button, a buy button. We see a list of transactions, some Bitcoin incoming, some Bitcoin outgoing, and we see a nice balance of how much Bitcoin we own. We can take a look over here. These are just some of the pros of BRD. And there were some other types of wallets, right? We go back to the Wizard, and there's mobile wallets, but there's also desktop wallets and hardware wallets. Let's check out each of these just arbitrarily. I have a Mac, so I'll click that. I'll say I'm new again. We'll skip these options again, and let's see what we get. We see that we have BitPay and Electrum. I'm actually going to click on this and this to get a more fleshed out list of desktop applications. And we see that we have a couple more options. Let's click on Bitcoin Core to check out what this is. And it says Bitcoin Core is a full Bitcoin client, backbone of the network, high level security, privacy. It has fewer features and it takes a lot of space and memory. Wow, a lot of space. That kind of reminds me of maybe a full node. A lot of space. The blockchain has a lot of space, so maybe it has something to do with that. We come over here and we see that this wallet is a full node. That means it downloads the entire blockchain. That means it's pretty secure. You know, we have the entire blockchain to verify transactions against, and we don't have to trust other nodes to give us block headers to verify the transactions we want to verify. We do see, however, that the UI is a bit lacking. It's a bit rough around the edges. The other app looked a lot cleaner. Keep in mind, this is on a Linux operating system, so this is on the desktop. We see this button called source code. Let's just quickly take a look here, and you see that it opens a GitHub website. And so this is actually the entire open source code of the Bitcoin Core app. Anyone can go in and audit the code. This is the exact same code that'll be running on your device if you choose to use this wallet. And that's really cool. They're completely open. They know that transparency is key, and so they have this available for users to look at. We'll go back to the Wizard, and let's check out that third and final type of wallet. It was, oh yeah, a hardware wallet. I don't even know what that is. Let's check out what a hardware wallet is. You see that it's only available for experienced users. New users can't even use it, so that's kind of scary. Let's go in. A couple of options. I'm not going to touch those. And we see that they were outputted with this list of hardware wallets. Let's just click on the first one, Bitbox02, and check that out. A lot of words, USB-C, interesting. We go down to the picture because pictures are nice. And we see that this looks different than all the other wallets that we've been looking at. The past wallets were iPhone apps and desktop apps, but this looks like a USB, which doesn't really make a lot of sense, but actually it does make sense. Because remember, wallets just hold your private and public keys. Your private and public keys, as I showed you in the previous slide, it's just a string of alphabet letters and numbers. A USB could hold that, and so that's kind of what this hardware wallet is. It just literally just stores your private and public keys. You see over here, full control of your Bitcoins, complete transparency. Very cool, very cool. I'm going to transition back to our slides, and we'll talk about these different types of wallets that we just saw. So what's up with that? Why are there so many different types of wallets? Well, we can see from this very nice and clean tree diagram that Bitcoin wallets are divided into hot wallets and cold wallets. And we see a familiar hardware wallet over here. We see the familiar Bitcoin Core wallet over here and the BRD wallet. And these are all in like different categories. They're all in like leagues of their own. And I'll go into each of these in this lecture. So let's go in and go to the next section. Hot wallets. All of these wallets on the left side over here, these wallets are wallets that are connected to the internet. That's it. In some way, shape, or form, they're connected to the internet. And we see that, you know, the iPhone app connected to the internet, the Bitcoin Core wallet connected to the internet, Coinbase connected to the internet, and also Edge is connected to the internet. So what does this mean? Well, it's connected to the internet, and so it's able to, you know, send and receive transactions very easily. It's very easy to use one of these wallets. We just kind of, in this case, we download the app. In this case, we download the program. Over here on Coinbase, we're going to be signing up for an account and using sending, receiving, buying, selling Bitcoin in that way. Now, cold wallets, on the other hand, are completely disconnected from the internet, or not completely, but to some extent disconnected to the internet. And so we see paper wallets is an example of that. The hardware wallet we saw is an example of that. And the brain wallets, which I'll go more in depth into, is an example of that as well. These hardware wallets, it's kind of like a USB. They connect directly to your computer, and you're able to you know, during the setup, you know, set up some private keys and public keys. And then I'm pretty sure that while it's connected to the computer, it can use some software on the computer to, you know, connect to the blockchain for a small amount of time just to, you know, maybe update the amount of Bitcoin you have or send and receive a transaction. But when it's disconnected from the computer, there's no Wi-Fi adapter, there's no connection to the internet when it's disconnected from the computer. Another type of cold wallet is a paper wallet. And so like I said before, and I keep saying again, wallets just hold your public and private keys. And so why not just print that on a piece of paper? And that's exactly what bitcoinpaperwallet.com does for you. It'll randomly generate a public key, private key pair. It'll print it on this nice Bitcoin design wallet. It'll give you a nice QR code, so you don't have to type in your very long public key every time you want to receive or send some Bitcoin. And what this does on the website, it actually even says, you know, users who are using this wallet should, you know, load the website, load the JavaScript, and then turn off your internet, turn off your Ethernet, your Wi-Fi, whatever, so that you're completely isolated on your own computer, so that you're sure that no one can be snooping on your computer. You know, there's no hackers or any malware that are broadcasting your screen to a remote location, as it says right here. And so you just go offline, run this paper wallet generator, so then you have a complete cold storage wallet that is unhackable, because you can't really hack a piece of paper. Brain wallets are another super interesting concept. And you see on the right that there's like a list of 12 random words, and maybe you're wondering, like, how does a list of 12 random words lead to a private key, public key pair? Well, brain wallets are a mnemonic, or a collection of words and phrases. It's a convenient way to memorize your private key, because, you know, for humans to memorize like a 32 like random letters and numbers, it's very hard. It's much easier to memorize just 12 words. So it's easier to have something that you can turn into your private key. But, you know, it's not as secure as we think. You know, you might think that it's in your brain, no one can hack your brain, but, you know, number one, humans aren't as random as we think we are. We're pretty deterministic. And if you have a bad memory, you might not want to use this method, because if you forget your private key, then you do lose access to your funds, just like your real wallet. And so the process of turning these 12 words or phrases into a private key kind of goes like this. You know, memorize your random words and phrases, and you can turn it into a private key using the hash function. Now, we've talked about a hash function in previous lectures, and the idea behind the hash function is you take some input, doesn't matter what it is, basically it's just some amount of data. You run it through the hash function, and the hash function outputs random data, a random string of alphabet letters and numbers. And so what you do with a brain wallet is you memorize those 12 words, or however many number of words, put it through a hash function, and there's your private key, and then you can derive a public key from that. And so you might be wondering, why are there so many different types of wallets? Why not just use one type of wallet? Well, let's take a look at this spectrum. We have security on the left, and we have convenience on the right. And so one might put the Coinbase wallet or Coinbase web app all the way on the right for convenience, because it is pretty convenient. All you have to do is log in like you would log into any other web app, you know, maybe using Facebook or Google. You have an account, you verify your account, and bam, you're able to buy and sell Bitcoin. You can send Bitcoin to whoever you want. You can receive Bitcoin from whoever you want. Very convenient, very easy to set up, very intuitive, because we use web apps on the daily anyway. All the way on the left, maybe we have a hardware wallet, since, you know, it's a little bit weird to think about using a hardware wallet to send and receive transactions. And the setup can be difficult as well. You have to, first off, buy the wallet, and then you have to use some software on your computer to set it up and input your private key and your public key. You can actually send and receive transactions. Some hardware wallets have like a little OLED screen on the USB itself that you can use to choose options and mess around with like that. But many people would say that it's much harder to use than for example, a web app or a mobile app. But in fact, it is much more secure than using a mobile app or a web app. In the case of Coinbase, by logging into the web app, by logging in using your Google, Facebook, or an email password pair, you're basically giving all of your information to Coinbase, and you're trusting that Coinbase won't get hacked. They won't leak your information. They won't sell your information to, I don't know, marketers or advertisers or whatever other companies. Additionally, with Coinbase, you have to go through a process where you have to, give them your passport or some sort of identification for government regulation. It's a lot of personal information, basically. And you're giving this all to this third party, this company that will, in the end, make your Bitcoin experience easier for sure, but not as secure. While on the other hand, hardware wallets, like I said, disconnected from the internet, pretty much impossible to hack into. I'm not going to say impossible, but much harder to hack into, much harder to access without the proper authentication. And then somewhere in the middle the Bitcoin Core wallet and wallet apps. It's a spectrum, right? So you kind of get convenience for giving away security. Maybe with the app, you're trusting the app developer to not mess with your data, stuff like that. And so this idea of security versus convenience comes up a lot in Bitcoin and blockchain ideas in general, right? As users, it's up to users to kind of take it upon themselves to be responsible, to be knowledgeable about the dangers and the different ideas regarding security versus convenience, and to ultimately choose the wallet that's right for them, maybe using the bitcoin.org website. Any questions so far about different types of wallets? Let me check the chat. Unfortunately, I can't actually open the Q&A without leaving the screen, so I'll just check the chat for now. Yeah, Kentaro. So Kentaro asked, is there some sort of app stored in the hardware wallet with the GUI that runs when you plug it in so you can easily send, receive, etc.? I encourage you to check out the many hardware wallets that are available on the market. I haven't done too much research on hardware wallets, but I do know some of them provide a companion app that you can download and install on your computer. And so when you plug it in, it's able to interface with your hardware wallet, and you can, send, receive transactions while you're connected. And then when you disconnect, it'll go away and you can't really use it. But yeah, definitely hardware wallets have a companion-like app that allows you to send and receive transactions. Yeah, and Kentaro asked another question, a string of questions actually. How do hardware wallets update the information for the user? I think this differs between hardware wallets. I haven't, like I said, looked into hardware wallets or bought one. I really do want to though. I'm gonna check that out. But yeah, I'm pretty sure when it's connected to the computer, it's able to use the computer's Wi-Fi chip, the computer's connection, and update the Bitcoin balance and send transactions, stuff like that. Is it only possible to send and receive information while the hardware wallet is connected to the computer? Again, this differs. I believe there are some hardware wallets that have Wi-Fi or Wi-Fi capability, so you can like mess around on the hardware wallet itself and send transactions. But I think they're so small. I think for ease of use, you would want to use the computer with it. Check out Tezos. I think Tezos is they have like a more functional hardware wallet where you don't need the computer itself. So another question was, if the hardware app is just the private and public key pair, why is the USB so big? Can't it just be really small since it's just the two 256-bit strings? Yeah, so we'll learn later on that it's not just two keys that you store in your wallet, or hopefully it's not just two keys that you store in your wallet, because in general, you want to be using a new public key for each transaction. And in general, yeah, I'm not really sure. Actually, you could have one private key or you could have multiple private keys. But yeah, in a hardware wallet, you want to store more. You're probably going to be wanting to store more than two keys. And also, it's like, the hardware itself, the hardware wallet itself has to have, programming and programming built in to interface with the computer. Some hardware wallets also have LED screens or OLED screens, like I said. And so the reason that a USB might be so big is just to have that extra functionality. And also they definitely have like encryption algorithms and fail safes to make sure that your so that the connection is very secure and it's not able to be hacked. Do most hardware wallets store non-full nodes? It seems like a lot to store a physical copy of the full blockchain. That's a very good question. Hardware wallets. I think again it depends on implementation. I would have to look at the specific hardware wallets to see how they run. But that actually reminds me of a good point that these Bitcoin wallets, the Bitcoin Core wallets, like I said, like it was mentioned in the Bitcoin.org website, it's the actual full blockchain. It's a full node. You're running a full node when you download this wallet. You have the full blockchain at your disposal. You're checking, you're verifying, you're mining, and all that. Coinbase, on the other hand, is not really a type of node. Basically, what you're doing is you're trusting in Coinbase, and you're giving all the responsibility of verifying transactions, of doing all the things that a node should do to Coinbase. So this is kind of like a similar idea amongst different web wallets. All you have to do as an end user, all you're allowed to do kind of is just transact. You can just send Bitcoin, receive Bitcoin. You're not really contributing to the network. And so the Coinbase web app, you're not really running a node at all. BRD, on the other hand, I'm not exactly sure about the implementation, but if I were to take a guess, I would say that these are running an SPV node. So because it's on your phone, obviously it's definitely not a full node because you don't want to download the entire blockchain, but maybe on your phone, you want to be doing peer-to-peer verification of transactions real time with block headers and blocks that are sent to you like that. And so this is the point I'm trying to get at, is a wallet isn't just one type of node. Wallets can be used on top of different types of nodes, and it's just the idea of storing your private and public key. All right, it seems like most of the questions are being covered by the education department. We'll go ahead and go to the next section just for the sake of time. So this next section is acquiring Bitcoin. Now that we know about wallets, how do we actually get Bitcoin to send to friends named Diego? Just like there's different types of wallets, there's many different types of places to actually acquire Bitcoin. One of them being a Bitcoin ATM, and it's pretty much exactly what you think it is. It's a physical location. Here are some locations around the Berkeley campus. You can find a Bitcoin ATM near you. I think the URL is coinatmtrader.com. Basically, what you do is you go up to one of these ATMs. You input your public key, your Bitcoin address. You can type it in, or maybe scan a QR code that you got in from your paper wallet. And so once the Bitcoin ATM has your public address, your public key, you can choose how much Bitcoin you want to receive, or choose how much Bitcoin you want to sell. If you're trying to buy Bitcoin, you input your cash or whatever, and then that's it. The transaction is handled by the Bitcoin ATM, and you receive Bitcoin in return for cash. Very simple, very cool, very cool. The next type of Bitcoin, the next type of method to acquire Bitcoin is through centralized exchanges. Centralized exchanges actually do exist. We've been talking about one in Coinbase for quite some time. Some examples of the centralized exchanges, like I said, Coinbase, Kraken is another one, Bitstamp is another one. Different exchanges work differently, but from a high level, it's comparable to a stock market where users can make an order for Bitcoin, either buy or sell, and the exchange itself will execute that order at the market value. The liquidity in these centralized exchanges are provided by the exchanges themselves. So the exchanges kind of handle everything in the back end, and you're just the user interfacing with it. Hopefully some of you this is kind of already raising some red flags in your mind, because this is less than ideal because it's centralized. You're giving all your information to the company. You're entrusting the company to follow through with your transaction and do all that. And so there's a lot of centralization going on there, and we as Bitcoiners don't really like that. Again, bitcoin.org has a list of exchanges you can check out. And yeah, on the other hand, decentralized exchanges also exist. These decentralized exchanges are basically what happens in decentralized exchanges is you're kind of paired up with another user who is trying to do the opposite of what you're doing. So if you're trying to buy Bitcoin, it pairs you up with a user who's trying to sell Bitcoin. You're selling, buying Bitcoin, vice versa. And so what this does is it minimizes the middleman that's necessary. So it's peer-to-peer. That's the point of decentralization. And you're interacting directly with another user. And so you can see that, this is very decentralized. The exchange itself isn't really, that doesn't really have access to your personal information, or not as much as a centralized exchange. The decentralized exchange itself isn't like executing transactions and checking all those. And the liquidity in a decentralized exchange is provided by its users, compared to a centralized exchange where it's provided by the company. And so again, this idea of security versus convenience comes up again, and I'll show you the spectrum once again. All the way on the right-hand side is convenience. Coinbase was here last time, and Kraken is here again. Just to distinguish between Coinbase, the wallet, and Coinbase, the exchange. That's why it's in both places. But basically, with Coinbase and Kraken, it's, again, super easy to get set up. You're just logging in with your email password. You're just buying, selling Bitcoin, not really wondering about the behind the scenes, and Coinbase, Kraken take care of all that for you. And so it's very convenient, also not very secure because of the reasons mentioned earlier. You're trusting a third party. That's generally a no-no. With decentralized exchanges, it's you interacting with another Bitcoin user. There's very little middleman, or as little middleman as these implementations try to get to. It's pretty secure because of that, but it may be a little more of a pain in the neck to set up, to actually use, to actually send Bitcoin, to actually receive Bitcoin. So this is the same idea of trade-off, and the same idea of user preference, and it just goes to show how important it is for users who are actually trying to acquire Bitcoin and trying to use wallets to just be knowledgeable and to make these decisions, make these educated decisions for themselves. Any questions about exchanges? What kind of transaction costs are involved? Very good question. You're thinking outside the box. Yes, in the Bitcoin network, there are transaction fees. These are very important to the network, and they're only growing more and more important because of the nature of Bitcoin. But we'll be going to that in the mining section. Diego actually had a couple of slides on that. So yeah, don't worry, your question will be answered. Okay, just for the sake of time, I'm going to continue. Hopefully our education team can take care of the rest of the questions. Hopefully the Q&A is also being answered. This short segment is just to show you guys how easy it is to create a wallet. I think there's a lot of misconceptions, about using Bitcoin. I feel like when someone first hears Bitcoin, maybe it's like the idea of a programmer behind a computer screen on the terminal, typing away and trying to access Bitcoin or something. But it's actually, in this day and age, very, very easy to create a wallet. Our first example is going to be the paper wallet that we talked about earlier. Walletgenerator.net is another example of a wallet generator, in a sense. What this cool website does is you can go to the website, you click on random places on the website, and the idea is from these random mouse locations, it's able to take the coordinates on the screen and generate a random string of letters and numbers, and that becomes your private key. I encourage everyone to check out this website. It's really fun to play with, and it's really fun to go through the process of creating a wallet. And yeah, a really cool exercise. Blockchain.com also has a wallet. You can go to this link and set up a wallet. Basically, it's very similar to signing up for any other service. You input your email sends you a wallet ID. You input the wallet ID here just to verify that you are indeed the owner of the email. Set up a password, and then bam, you're greeted with a dashboard that has some different types of currency. This is not only a Bitcoin wallet, but also ETH, Bitcoin Cash, Stellar, Algorand. These are examples of other coins that you can hold. These are other coins that are on the blockchain. And you can see that this is the current price of Bitcoin at the time of screenshot, I guess. And yeah, it's literally just a couple of steps to set up a wallet. That is if you're using a web wallet, right? So if you want to set up the Bitcoin Core wallet, you would have to go to Bitcoin Core GitHub, read the docs, and figure out how to set up a full node so that you can have access. So you have the entire history of the blockchain downloaded, and set up like the BRD app using to set up a Bitcoin wallet on your phone. You can use the BRD app and set up a wallet that way. So yeah, many different ways to set up wallets. And this is just another screenshot of the blockchain.com website where you can pretty much immediately just request Bitcoin from people and send Bitcoin. Any question about this very short segment? What's my favorite wallet and why? I mean, that's a very opinionated question. I have to go with the Bitcoin Core wallet. That's the just because that has the Bitcoin. It has the support of the Bitcoin developers behind it. You can see on GitHub, people are working at it. People have put hundreds of thousands of man hours into it. That has the actual code that Satoshi started off with, and that's all been transferred to GitHub, and thousands of people are contributing to it every day. It's open source. I can see what's happening in the code. I actually have it installed on my computer. It's really cool to see a full node running on your computer, even though it's taking up a lot of storage. So that's kind of yikes. But yeah, I have to go with the Bitcoin wallet. Full node is the way to go if you're looking for security. That's it's top of the food chain right there. Nishon is shouting out Ledger Nano S. I've only seen a couple of pictures. I definitely need to look more into hardware wallets. All right, this is a relatively short segment, so we'll go ahead and go into the next section. Wallet mechanics. Multi-sig, multi-signature. Now, we haven't talked about multi-sig too far, but it's a commonly implemented technique in wallets. Multi-signature, which allows for M of N transactions. It's a way of cryptographically sharing a key between participants. And it serves to distribute points of failure. So in these, you'll hear this term a lot when you're learning about Bitcoin. It's like distributing points of failure. It's like you don't want to have all your eggs in one basket, because if that basket drops, then all your eggs are gone. But similar to that, you don't want to have the only key to your wallet to be owned by you, because I am very forgetful and humans are very forgetful and error prone. So maybe you want to have a multi-sig wallet or multi-sig address. And so what this allows you to do is, say you were sharing your wallet with your family or even with yourself. But an example of this would be like Coinbase. Coinbase provides a service where you can do 2 of 3 or 3 of 5 multi-sig. And so in 2 of 3 multi-sig, you keep 2 of your keys and Coinbase holds on to 1 of their keys. But say I lose 1 of my keys, then Coinbase will step in with their key and help me access my funds. Usually when you're using a wallet and you lose your key, you lose the password to your wallet or you lose access to your wallet, then your funds are gone. In multi-sig, however, you're able to kind of have a layer of fault tolerance there. You're able to kind of prevent prevent that from happening because you're distributing points of failure. And so if I lost a key just by myself in my own wallet that I was running by myself, all my Bitcoin's gone. I'm just down all that Bitcoin. But because I have another person, another entity that holds a key, assuming that they didn't lose their key, if I lose one of my keys, I'm able to access my wallet with my key and their key. And I didn't explain this very well, but in a 2 or 3 wallet, you require 2 out of the 3 keys to access a wallet. And I'll get more into that in this example. Say Justin right here wants to unlock a wallet and send some transactions to Rusty over here. He can't do that. He only has 1 key, but this is a 2 or 3 wallet. On the other hand, Janice and Oscar can use their 2 keys to unlock the wallet, access the funds, and send it on over to Rusty. So multi-sig is a really cool idea, and you'll see it everywhere when you're researching wallets. Best practices regarding wallets. Probably the number 1 rule is to never reuse pseudonyms, or this is mainly to say always reuse public keys, or never reuse public keys, sorry. You should be, with every transaction, generating a new public key from your private key and putting that out there onto the blockchain. Now, why do you want to do this? Well, the idea of anonymity in Bitcoin only works if you as a user are responsible enough to kind of execute on that idea. Someone should not be able to determine how much Bitcoin you own ever. If you use the same public key with each transaction, or say like a bunch of people sent you money and they were all sending Bitcoin to the same public key, well, I mean, the blockchain is available to everyone. Anyone can look through it and anyone can see where Bitcoin is coming from and where Bitcoin is going. That's kind of the idea of a distributed ledger. On the other hand, if there's like a bad actor or like a bad agent or someone who's trying to attack the network or attack you personally, they can just see like, oh, there's a lot of Bitcoin going to this public address. They can even calculate how much Bitcoin is going because that's also available on the network. And we don't want that to happen. That kind of defeats the purpose of anonymity and privacy. And so to prevent that, always generate new public keys, new receiving public keys and new outgoing public keys whenever you're enacting a transaction. Keys are computationally easy to generate anyways. You're just kind of hashing something, usually your private key, and that's very simple to do. Run it through a hash function and bam, you're all good. And usually wallet software will handle this. Most wallets have this built in. You don't even have to worry about 256-bit long strings. You just click send, click on Diego, send him some Bitcoin, or like you're not thinking about it. Wallet software will handle this for you, which is why wallets are so great. But the question is, how do wallets do this? How are wallets able to, continue to generate keys at a low cost and at a quick rate? Well, there's these things called, there's this idea called hierarchical deterministic wallets, HD wallets. And the idea here is that you have one private key, this key right here, which is generated from some random seed. And using this private key, you're able to generate a bunch of child private keys and a bunch of matching associated child public keys. It's deterministic because all child keys are generated from that one seed, that one private key, the same way, the same time, every single time. And hierarchical because you can organize the keys in a tree-like structure with levels, as you can see in this diagram to the right. And the advantages of a tree-like structure, I'll explain in 2 slides. And so how, actually I'll explain it in 1 slide. So there's fewer points of failure. So this actually kind of goes both ways. It's a double-edged sword. You're only storing or backing up one master private key. You only need to keep track of this key because the rest of the tree, the rest of the keys can all be generated from this one key. That's the only one you need. But this could also be considered a flaw because you lose this one key, you kind of lose everything. And so you want to make sure that you have a lot of backups of that private key and it's very safe and secure and tucked away in a safe place. Additionally, access control. The tree-like structure can allow the owner to allow someone access to only part of the wallet by delegating them a certain branch. So instead of, say you want to give your kid access to just a couple of funds, way in the future, maybe you'd only give them this key so they can only access this branch of private keys and thus the Bitcoin that's associated with this branch of public keys. And so it's a really cool idea with HD wallets. But how do HD wallets work? So this is a black slide, which means that it's a more technical slide, but it's not too technical. We'll just be hitting a high-level overview. So first, we start off with a master private key. How do we get this master private key? We want to generate a random seed. Randomness is very important because humans are pretty deterministic. From this random seed, we generate a master private key. Child private keys are generated by hashing your private key and an index. So for example, these keys down here, actually, I'll talk about these keys. So imagine there's right underneath this private key, there's a couple more child private keys, going down here. The way you would generate those private keys is by using the hash function. And so the idea of hash function has come up a lot in this lecture. It's come up a lot in previous lectures, and it'll come up a lot in lectures ahead. Hashing functions are very important. The general idea is that you input some data and it outputs a random alphanumeric bit string. Two key concepts to remember here are the avalanche effect. And so what that states is that with a hash function, changing just even one bit, changing a small amount of the input will result in a completely different output. And so you can see that idea in action here. We generate private keys by hashing the private key and the index of the child key. So say we have a child key at index 0, a child key at index 1, 2, 3, 4, all the way down. What we would do to generate these private keys is run the private key, what we would do to generate these childs is run the private key plus 0, and that's the hash. And then private key plus 1, that's the second private key, or child private key. Private key plus 2, that's the third child private key, and so on and so forth. The second idea of hash functions that you should keep in mind, and you can see is applicable here, is that given a hash function, given the same input, you will always receive the same output. And so that's important in this case because I said that you can regenerate this entire hash tree given just one extended private key. And that's because of this definition of hash functions. The same output will always result in the same input. And so, and it's deterministic, 0, 1, 2, 3, 4, 5. Given just this one private key, you can generate all the child keys and all the corresponding public keys. And that's a really cool concept. And that's one way that wallets kind of generate new keys for each new transaction. Any questions? That was a bit of a technical slide. And also feel free to ask any questions about wallets in general, because this is the final portion of the wallet section. Oh, actually, I can check out the Q&A now. I'll let Diego start sharing. Stephen Bauer asked, can one trade on an exchange in a different country than where the trader is physically located? Yeah, I'm sure you can, spoof your location to trade in a different exchange, but yeah, you generally, I guess if you need that, if you really want to trade on a different exchange, you could. There's always ways to find loopholes.
Sagan, can you see my presentation?
I can hear you perfectly. So we're all set.
I think I should start because we have 35 minutes. So
I'm way over. Go ahead. Yeah.
Cool. All right. So hi everyone. I'll be going over mining. So let's get started. So mining is a protocol to add information to the ledger. It's kind of this secure way that all the miners in the Bitcoin network agree on, in which they want to add new transactions into the blockchain. So mining is the way that we update the blockchain network, the Bitcoin blockchain. So the miners will be verifying transactions and then adding this into blocks, and then they'll be adding new blocks into the blockchain. And something key about mining is that mining is the way through which we introduce new Bitcoin into the Bitcoin network. So as we will explain in future slides, miners will receive a reward that we call a block reward whenever they successfully find the nonce of a block. And then when this block is added into the blockchain, this will increase the supply of Bitcoin in the entire network. So this is essentially how all the Bitcoin has ever been added into the Bitcoin network. So let's get into it. Cool. So let's go over a quick overview on recipe for mining. So as Sam briefly mentioned this before, but there are light nodes and full nodes. So full nodes is are essentially our miners. So the first step that every miner needs to do is to download the entire Bitcoin blockchain. They need to have the entire transaction history of all the transactions that has ever been processed in the Bitcoin network. And this is kind of a prerequisite for mining. After that, once you have downloaded the entire Bitcoin blockchain, you need to be essentially listening and hearing for incoming transactions. So if I think Sayan has sent me a lot of Bitcoin throughout the presentation. So if I want to send him some Bitcoin back, then I would broadcast this transaction to the network. Essentially, will go into something called a mempool that we'll discuss later. And then the miners will be able to see all the unconfirmed or pending transactions. And then they can grab some of these transactions, put them into a block, and add it into the Bitcoin blockchain. So this is what we mean by listening for and verifying new incoming transactions. So after that is, I think I already mentioned this, but you want to create a block using this list of incoming transactions. And we'll talk, I think you guys already learned about Merkle trees, which is how we organize the transactions in a block. And then we'll try to find a valid nonce. So this is essentially solving a cryptographic hash puzzle. And it's like throwing darts at a billboard, right? And you want to use all your computational power to find a valid nonce for a block. And once you find this, you will broadcast your block to the network, and hopefully everyone will accept it. All the math will check out, and it will be added to the blockchain. So once this happens, you will receive some profit. So something I wanted to also touch briefly on is mining is a competition, right? So you are competing with other miners in order to find a valid nonce. And also something key, which I think you already learned from previous lecture, is that the longest chain wins, because every block, like you are proving that you did some kind of work to add that when you find the nonce for a block. So the longest chains is the chain with the most amount of work, essentially. So I guess a question that many people ask sometimes is, let's say I'm a miner, Sayan is another miner, and Sayan finds a new block, right? And they find a valid nonce. Why do I need to accept his new block? And the reason for this is, if you don't, you're just gonna fall behind, right? Like the blockchain that you're mining on is gonna be smaller than the new updated one that all the other miners are mining on. And yeah, you're just gonna fall behind. So like, I guess an incentive is that you always want to immediately get the new block and start mining again. So now I'm gonna get into each of the specific details on this. So cool. So yeah, as I mentioned, the first step is downloading the blockchain. So I guess all the miners started at the Genesis block, which is the first block in the Bitcoin blockchain. And then whenever someone else finds a valid block, I will verify it. And then I guess the network will verify that everything checks out, that they actually found a valid nonce. And then this will be added to the blockchain. Once that is done, you would essentially, as a miner, download that into your local copy of the blockchain and start mining based on that. And yeah, I think this is, as I mentioned, this is a prerequisite for mining, and it's a way, yeah, we get blocks from peers. So cool. The next step, as I mentioned, is we need to verify the transactions. So there is a mempool, and I'm gonna explain this further. So a mempool is just a list of all the unconfirmed or pending transactions that are sitting in this mempool. And me as a miner, I can go into this mempool, and I think currently the number, like the average number of transactions that have been included on a block has been around 2,000 recently. So let's say I want to grab 2,000 transactions from this mempool, and then I'm gonna essentially verify them and start constructing the block. So I guess a question that many times occurs is, let's say that there's a cap on the number of transactions that you can include in a block. So let's imagine there's 4,000 transactions in the mempool sitting there, but I can only include 2,000 in my current block because there's a 1 megabyte memory limit on the size of the block. So how does a miner choose which of the 4,000 transactions they want to include? And this is where transaction fees come in. So we'll explain this further in other slides, but in addition to getting a block reward every time you find a valid nonce for a block, you would also get a reward for all the transactions that you added into that block. So essentially miners will always want to just get transactions that have the highest fees, and then you can, because this will maximize your profits. So cool, let's get into creating a block. So once we have verified the transactions, making sure that everything checks out, we would gather them into the Merkle read and Merkle tree, sorry, and then create the Merkle root, which is included in the block header. So I'm not going to go into like the data structure itself because I think you already covered it. But something I did wanted to mention here is, if you can look where my mouse is, there is a Coinbase transaction. And a Coinbase transaction is kind of a right that every miner has to include a transaction into the block. And this transaction is a transaction to themselves. So the miner will be sending to themselves a specific amount of Bitcoin because they were the ones that found the nonce of this block. And this is what we know as the block reward, which we'll explain more later. But yeah, this is essentially how a new Bitcoin gets added into the Bitcoin network. And yeah, let me see if I missed anything, but yeah, and then obviously you want to include all the metadata like the previous block hash and all that information into the block itself. So now you constructed the block. Now we need to go and find a valid nonce. So this is where proof of work come in. You need to use all your computational power, all your CPUs, ASICs, all your GPUs, whatever you have in order to start mining, right? So as we mentioned, this is a brute force algorithm, right? There's no intuitive way to go about how to find the nonce here. You will need to find a nonce such that the hash of that and other information such as the block header and the Merkle root are less than a specific target. And you can think of a target will be just a string with a certain X number of zeros at the beginning and then a lot of other bits later. And you just want to find a nonce that makes the hash of the block header and your nonce to be less than this target. And I think there's like the amount of work that you need to do is 2 to the X, where X is the amount of zeros in the target. This is not as important, but and you can look at the code if you're interested. I'm not going to go into it too deeply, but yeah, this is where you solve your cryptographic hash puzzle. And as I mentioned, it's like throwing darts at a board. And I guess another interesting thing is the difficulty. So you can change the difficulty of the cryptographic hash puzzle, because if the hash rate of the entire network is increasing, then you want to make it harder that for the miners to find a block, because the idea is that a new block is added every 10 minutes, right? So you can think of the difficulty as the number of zeros at the beginning of this target. And yeah, this is adjusted, I think, every 2 weeks, if I'm not mistaken. But yeah, let's get to the other steps. So now I have, in this case, Janice have found the nonce of a new block, and she wants to broadcast this into the network. So Diego gets really sad because Janice bid him, well, bid me, I guess, into finding the solution of the block. And yeah, you want to broadcast this information to the entire network. So after you broadcast this information, everyone can validate the information, check that actually the nonce that Janice is claiming to have found is actually results in a block header that is less than a target. And also, in this case, Andrew is checking out that the Coinbase transaction is for an amount that the current block reward is. Like, imagine they just want, Janice decided to add 1,000 Bitcoin to her account. Well, that's not gonna check out. Like, we're not gonna accept this block if that happens. So yeah, and then Erica is just checking that all the transactions are valid. And if all this checks out, then essentially we come into a consensus and add this block into the blockchain. And now we have successfully added a new block, and the entire process starts again. We're gonna start mining again. So with this, yeah, the final thing that I already mentioned is mining is a competition. The longest chain essentially wins, or is the most updated state of the Bitcoin network, because it has the most amount of work in it. And yeah, I think I'm gonna see if there's any questions, which I think there is. Okay, I think a lot of people are already answering these questions. So if 2 people announce a block at the same time, so if 2 people actually, that's a good question. Like how would we? Yeah, I think I don't know exactly what's the algorithm to determine like at what timestamp one miner found a valid nonce compared to other ones. So I will need to get back to you on that. Not exactly sure how that is working. So yeah, I'll let other members answer that. So let me move on because we do need to cover other stuff. So yeah, now I guess a question I have for everyone is, what are the incentives for miners, right? I think I mentioned already the block reward, right? So that is money that you're receiving, kind of a transaction between, oh, I'm using all this electricity, all this hardware, and I'm getting Bitcoin for it. So that is an incentive. But you know, what do humans like? And I think it's pretty easy, right? Profit. Like that's yeah, I guess that's a big incentive for miners to be part of a system, right? Because they're getting profit and a lot of profit. So yeah, miners want a lot of profit, a lot of Bitcoin, a lot of money. So yeah, I guess this comes as a game theory side of things. Like you want to maximize your profit, and that's what miners are trying to do. Now, how do we define profit? And it's pretty simple. Probably most of you are familiar with it, but it's just you look at your revenue, how much money you're generating, and then at your costs. If your revenue is greater than your cost, then we made some profit. So pretty straightforward there. So now I'm gonna go into what are the sources of mining revenue, what are the sources of mining costs, and you know that you can look at the if statement here that checks if the revenue is greater than the cost, then they actually made a profit, as I explained before. So the first source of revenue is the block reward. So let me explain that further. So every time, currently the block reward is 6.25 Bitcoin. So every time a miner actually finds the nonce for a new block, they're gonna include a Coinbase transaction, as I mentioned, of 6.25 blocks. Sorry, 6.25 Bitcoin. And then this is gonna be the incentive for them. So something curious, interesting is this year, the reward halved from 12.5 Bitcoin to 6.25. And this has been happening throughout the entire, I guess, history of Bitcoin. And around every 200,000, 210,000 blocks, there's a, like this halving happens. So in the next halving will probably be for 3.125 Bitcoin per block, right? No, it will be that, not probably. So I want to also touch a little bit on the graph on the left. So as we can see, as the Bitcoin supply increases, right? As I guess, and this is a function of time, right? The more time that passes, the more supply there's going to be in the network because the more blocks would have been mined. You can see that as this happens, there's like the block rewards decrease, and as you can see, they have. So initially started at 50, then we went to 25, then 12.5. Now we're currently at 6.25. And something very interesting is that by 2140, it will be the case that there is no longer more block rewards. So I think this is essentially shows that Bitcoin is a deflationary currency because there is a cap on the amount of Bitcoin that will ever be produced. So this is all this is saying. And I guess if you something cool, 6.25 Bitcoin is like 65K. So if you find a block, you get 65K. That's really nice based on the market price right now. So yeah, I guess a question that could get in here, what happens when the block reward, I guess the block reward gets to zero? Well, I'm gonna get into what other incentives are for miners in order to keep mining and I guess verifying transactions and keeping the network up to date. So cool, and yeah, this is just like, why is there a block reward? And the idea of all this is that through proof of work, we want to reward the honest nodes, like the people. The miners that are dedicated to the network have a like probabilistically are determined to get the highest amount of profit throughout time. If you're just a malicious actor, it is not like it, you will not be maximizing the amount of profits that you can generate. And yeah, this is just kind of the incentives for miners to be honest. Cool. So a question that I have for everyone is, I think, what is the incentive, specific incentive for miners, like to actually not mine an empty block? And what I mean by an empty block is miners could perfectly just have a mine a block that only has a Coinbase transaction, which is to them sending money to themselves, as I mentioned, but it doesn't include any other transactions. Like, what is the actual incentive in here for miners to include other transactions from the mempools? And this is where transaction fees come in. So in addition to block rewards, for every transaction that you include in the block, you would get a specific amount of Bitcoin. And this is something, if I'm sending money to Seiyon, I will specify a specific transaction fee that I want to pay the miner to include my transaction in the block. So it is in the best interest of the miners to also include transactions, like maximize the amount of transactions they can put into the block, because first of all, this is not increasing the difficulty of the hash puzzle they're solving. It's the same difficulty, but they are maximizing their profits. So this is a very subtle and important point that if there's questions, we can go back to it, but I think I'm gonna move on. So yeah, I think we already covered block rewards. Now we're gonna get into transaction fees, which are the other source of revenue for miners. So what are transaction fees? Every time, I guess the motivation for this is, as I mentioned, by 2140, there will not be, like, block reward will reach zero, so miners need other sources of revenue to keep operating. So the block reward, I guess, will, yeah, something that can happen is the transaction fees can increase as the block reward decreases, to kind of keep the incentive for miners to keep operating. So how do you specify the transaction fee in a transaction? So every transaction that you make has an input and an output. The difference between these two quantities is a transaction fee. So as you can see in here, we have an input of 5 Bitcoin, we have an output of 4.8 Bitcoin, and the transaction fee is 0.2 Bitcoin. So this is an extra income for the miners on top of the block reward. And something really interesting is the higher the transaction fee that you put, the more likely that your transaction is going to be included into your block in the next block. So you would like maximize the confirmation time. Like it will be the lowest confirmation time of your transaction as a function of the transaction fee. And yeah, I think something I just wanted to mention here again, I briefly mentioned this before, but let's say the mempool has 4,000 transactions. How do you actually choose only, let's say a block only can contain 2,000. How do you choose those 2,000? And the way the miners are gonna do this is they're gonna just get the transaction with the highest amount of fees so they can maximize their profits. And if I'm sending money to Seiyon, we're gonna get into this. I probably don't wanna put a very low transaction fee because then my transaction will never be included in a block. So me as a sender of Bitcoin would also be incentivized to kind of put a good transaction fee there so that there is a high probability that it gets included into in the next block. So let's actually discuss that. So how do we estimate the transaction fee that we're putting on of a transaction so that I guess we guarantee that the transaction I'm sending gets included sometime soon. So this is where we get into fee estimation algorithms. So a fee estimation algorithm will take in a target, and this target essentially represents the number of blocks that you're willing to wait for your transaction to be included. So if my input to the fee estimation algorithm is 5, then that means that I want my transaction to be included sometime in the next 5 blocks. Now, how do we calculate the fee based on this algorithm? And if I guess you can think of this as a black box. You give an input of a target, it gives you a fee. Now, the way this happens, I'll do my best to describe it. So the transaction fee algorithm is going to look at some recent history of transactions. So let's say you're going to look at the last 300 blocks in the Bitcoin blockchain, and then you're going to look at all the transactions that were included in those blocks. Those transactions have an associated transaction fee. So something important is this transaction fee is like, it's almost a continuous range because of the amount of, I guess, floating, the amount of decimals that it can have. So what we want to do is we want to put the transactions into buckets based on the transaction fee. And then the algorithm would essentially put this transaction into buckets, and then it's going to look at the lowest fee rate bucket where all the transactions in that bucket were confirmed within the target that I want. And also all the transactions in buckets with higher fees were also confirmed within the target that I wanted. So just to repeat that, the algorithm is going to find the lowest fee rate bucket where all the transactions were confirmed within the target that I specified, and also check that all the fee rate buckets with higher transaction fees were verified within that target. So this is essentially how fee estimation algorithm works. I'm gonna move on because we have 15 minutes. Cool. So now another problem that can emerge. Let's say I want to send a Bitcoin to Seiyon, right? Again, So I'm gonna specify a transaction fee, and I use the transaction fee algorithm. It's all good. I have very high confidence that it's gonna be included sometime in the next five blocks. Now imagine that after I send this transaction and include it into it's included in the mempool, a lot of people start sending a lot of transactions with high transaction fees. So what this is gonna occur is the transaction fees are gonna go high, and my transaction was included is gonna have a lower transaction fee. So it could be the case that it gets stuck in the mempool. And this happens, you put a transaction with a very low fee, it gets stuck in the mempool, never gets verified. And what happens if it's sensitive? Like it's time sensitive. I want my transactions to be verified. So this is where we get to fee bumping. In the case that your transaction is stuck in the mempool, there are two alternatives that we can use in order to essentially increase the fee and motivate miners or incentivize them to include our transaction in the next block. So the way to do this is replace by fee or child pays for parent. So replace by fee is what you want to do is you want to sign a replacement transaction with the same inputs, but paying additional fees. So the only thing this will do is it's going to replace the current transaction in the mempool with a new one that is using the same UTXOs, your same inputs, but paying additional fees. And the additional fee is going to come from the change in output. So if you lower the output, that means, remember, transaction fee is input minus output, then that increases the fee, and miners are going to be incentivized to include that. Now, the other alternative is called child pays for parent. So what you want to do here is now create a new transaction that is going to spend one of the outputs of the transaction that is stuck. So let's imagine I want to send to Seyon 3 Bitcoin, and I have an UTXO with 5 Bitcoin, right? So this transaction is going to send 3 to Seyon, and maybe it's going to send a 1.5 back to me after we send 0.5 as transaction fee. So if I consume the UTXO that will contain 1.5 Bitcoin, then this is a child or descendant transaction from the transaction that is stuck in the mempool. So I guess the reason this works is because miners can kind of combine transactions that have this ancestor and descendant relationship, and then kind of confirm them at the same time because one of them depends on the other. So you can think of this as a package. And if your parent transaction has a very low fee, then you can include a child transaction with a much higher fee, and then the miners will be incentivized to include this. And something very important is this only works if there is actually an output UTXO coming back to you. If there's no Bitcoin coming back to you, you cannot make a child transaction because there's no output that you can use. So I guess the incentive for this fee bumping solutions is that you as a user can initially just submit a transaction with a kind of low transaction fee so that you're not paying too much for the transaction to be verified. But then if it's never getting verified, then you can increase this fee and kind of guarantee that you're not paying too much for this. So that was a lot. Let's see if there's a lot of questions here. So yeah, I think everyone, we'll say on everyone is answering these questions. I'm gonna continue moving on because we have 10 minutes and we wanna cover other stuff. So thank you, education members. So now we have talked about revenue, let's talk about sources of cost, right? So there are fixed costs and variable costs. So let's talk about fixed costs for miners. So the fixed costs are generally just hardware costs, right? Like in order to solve the cryptographic hash puzzle needed, we need hardware, right? So this can be CPUs, GPUs, FPGAs, or ASICs, and we're gonna get into each of these. And something I wanna mention here is if you look at the total hash rate of the Bitcoin blockchain on the right, you can see that it's been increasing from 10 million terahashes per second. Currently, it's around 140 million terahashes per second. So it's been increasing a lot. And something to mention here is this is not increasing the throughput of the network. Like what this is just doing is it's increasing the difficulty of finding the nonce on your block. So that as we have more hash rates, then it's still probabilistically 10 minutes until we verify a new block. So this is not like making the network more scalable. It's just essentially using more electricity and I guess wasting more resources. But the network is getting much more secure. So that's important. Cool. So what is a CPU, right? Is the central processing unit of your computer. And yeah, this is at the beginning of Bitcoin. of the like closer, yeah, like in the recent years, most of the people were using CPUs to mine. I think Satoshi mentioned one CPU, one vote. So this was the idea behind this. However, then people noticed that we could use more powerful hardware. So they got into using GPUs. And as you can see, they're one order of magnitude faster than CPUs. There's a larger consumption of energy and higher production of heat at the expense of a higher hash rate compared to CPUs. You can see, yeah, that is one order of magnitude larger. And I think if the current time to block, like to find, if you use a CPU, the current time to find a block is around 7 million years. If you use a GPU, it's going to be around 700,000 years. And something to mention about GPUs too is they are many of the components in GPUs you may have heard of, like teraflops for GPUs, which is like the number of floating point operations you can make per second. Though those are not applicable for mining. So GPUs kind of were faster than CPUs, but also had a lot of wasteful hardware that was not very useful for mining. So now we can talk about a transitionary hardware, which is called FPGA. So it's a field programmable gate array, and this is kind of getting more into Bitcoin specific hardware. So CPUs and GPUs are what we know as general purpose hardware. Like you can put it in a computer and they can be used for you to play a game or to run an operating system, whatever you want. FPGAs and ASICs are optimized to do SHA-256 hashes at a very, very high speed and just literally used for Bitcoin mining. So you could think if the Bitcoin network goes down, FPGAs and ASICs will probably be worthless. So, but as you can see, the hashes per second of a FPGA is much more higher than a CPU and a GPU. And yeah, with that, let's get into ASICs. So ASICs is an application-specific integrated circuit. The only thing an ASIC will do is it will do SHA-256 hashes, and it's useless for everything else. So a good thing is it's much more energy efficient than a GPU, for example. It's gonna have lower electricity usage, and yeah, a smaller device, very high hash rate, and you can see a cost of here of the Antminer S9 is $1,500, so it's getting into the expensive side of things. So with that, let's go into variable cost. So this is the other source of cost for miners. So variable costs are things like energy, so the amount of electricity you need to pay to have your hardware running, cooling, and we're gonna see some pictures of some ASIC farms so that you can see the amount of cooling that you need in order to maintain a low, I guess, to reduce the heat or the temperature of your hardware. And infrastructure, right? Like many times you're gonna need to rent an entire warehouse in order to store all of your hardware and be able to do all the mining. And there was a very cool idea that if we have Bitcoin farms or ASIC farms in cold regions, then we can use the heat produced to warm as like, I guess, as a heat source for a house. So that's what they determined as data furnace, I guess, a house or a building. And that was pretty interesting in my opinion. And yeah, with this, right, so we covered this, I guess. Now you have the full picture of where revenue is coming from and where cost is coming from. If the revenue is higher than the cost, we get a profit. Cool, so let's get into questions. Okay, Sayun is doing a great job of answering all this. So yeah, Kentaro, how can you replace a fee if a transaction is immutable? Yeah, there's a process for that, and you should definitely check those articles. I think those will clarify a lot of the questions. So something I forgot to mention is you can think of a block reward as an exchange like between electricity and hardware costs and Bitcoin. So it's like this exchange of resources, if you want to think it that way. So let's get into real world mining. So how does an ASIC look like? Well, before that, this is a ASIC mining farm. So as you can see, these are racks of ASICs on the left image. It's actually a Chinese ASIC mining farm. And then you can see these huge fans that are just trying to get all the heat out of the warehouse and reducing the heat in there. And then on the right, we see two cooling systems. There's pretty fancy stuff with water and other, using other types of coolers in order to reduce the heat coming out of the hardware. So I think the current Bitcoin network uses as much electricity as Austria. It's like 1% of global electricity consumption, which is kind of crazy to think about. Cool. So yeah, I think this is how an ASIC looks like. So there's not much for this in this slide. Just wanted to show it to you all. There's a fan, and then you have a rack of all these ASICs doing all this hashing and computation. So let's get into the final slide here. So I guess a question that many of you can have is, if I'm a miner, right, and I have two ASICs, we saw that the amount of years before I expect a profit could be 10. Like, do I really want to make an investment and see a return on investment in 10 years? Or even worse, if I want to use a CPU, do I never want to see a return of investment on all the electricity that I'm paying for as a miner in the Bitcoin network? And it could be the case. If we just had like completely independent miners, this would be the case. Like, some of them would see extremely high profits every once in a while, where they mine a block and they get 65K, while others will never see a profit for a very prolonged period of time. So this is where the idea of mining pools came about. So essentially, a mining pool is a bunch of miners that are combining all their hardware resources and using them to mine as a single unit, I guess. And yeah, to mine as a single unit. And then if that mining pool is able to find the nonce of a block and solve the cryptographic hash puzzle, then the reward will be distributed between the miners. There's different like ways that this reward can be distributed between the miners, and we're gonna get more into mining pools in future lectures. There's proportional mining pools, pay per share mining pools, and they have different like incentives for miners. But I guess one of the downsides of mining pools is that the network is becoming more centralized, right? So you have this very centralized sources of hash power, and there's pool managers. So the pool managers will essentially publish a software that all the miners can download, and then they can use this to hash and kind of help the mining pool solve find nonsense for the blocks. And yeah, that's one of the cons. Like, it's becoming much more centralized. And in 2014, there was a very concerning situation in which ghash.io, which was a mining pool back then, got to 51% of the mining power in the network. So immediately when this happened, a lot of the miners in that mining pool left in order to prevent 51 double spend attacks, because they contain 51% of the network, which would have caused the Bitcoin price to plummet. And as you know, it is in the best interest of miners to keep the Bitcoin price high, because they're getting rewarded in Bitcoin. So with that, that'll conclude my section, and we can get into general questions for the last 2 minutes here. So Kentaro is asking, why doesn't Bitcoin and other coins require all miners to join a single mining pool to make a mining time faster if a coin wants to be more scalable? Are there coins that have this where they don't care about centralization? So yeah, I think that's a very good question. If you just have one single mining pool, then first of all, that will be completely centralized, and we don't want that. But I guess under that assumption, like if you just have one single mining pool, you can think about it as all the miners being completely independent. But then do you really wanna, yeah, like it just becomes really tricky, like how then you will distribute the money between one entire mining pool, because there will be a centralized, I guess, entity that will be in charge of organizing all the miners and distributing the money based on, I don't know how many hash power they contributed. And something to think about is, within each mining pool, there's like a specific hash ranges that a miner can try in order to find the nonce. So what in the mining pools, in order to prevent duplicated work, like let's say Sayan and I are on the same mining pool, in order to prevent us from doing the same computational work, the mining, the pool manager will tell us, Sayan, you're going to be in charge of trying to find a solution between this range of numbers. Diego, you're going to try to find a solution between this range of numbers. And then this is kind of how everything is organized. If there's just one single pool, I'm not exactly sure how that would look. But yeah, having more hash rate will not increase the scalability of the network at all. Like there will need to be something changed at the protocol level, maybe increasing the number of transactions that you can include per block or other stuff in order to increase the the scalability. Do you think there's a chance of a government interfering and using the mining pools to attack the network? I mean, it's extremely expensive. Like the cost of buying all the hardware, and like it's why would they do that? Like it will be, I think they could just put more regulation at that point. But yeah, bringing down the Bitcoin network, it would just be extremely high cost. And as I mentioned, like the amount of electricity per consumed per year is around the amount of electricity that Austria consumes. It's like 1% of global electricity consumption. So yeah, it's extremely unlikely. And again, and the hash rate increases, and you can see that it's been increasing really, I guess, fast recently. This will become, the network becomes more secure, and yeah, like it will not suffer from 51% attacks. So it is really not like, why would a government do that? I think there will be other ways to go about it, like increasing regulation.